Hello, everyone. Thank you so much for having me join APEC again. It's always truly a pleasure. Um, this is one of the funnest times, honestly, that I enjoy with research because APEC is such an open-minded community that this is kind of one of those chances where you can just share ideas, and even if traditional thinking would consider it to be ridiculous, we realize that there's a whole lot more out there to be learned and to be applied, hopefully. So without further ado, this is essentially like a part two talk for the last talk that I gave. This is all coming from this study on gravito-electromagnetic effects in superconductors. And this particular talk is attempting to make some connections to possible experimental manifestations. So I'd like to just mention that I do teach at Clovis College. I'm also affiliated with UC Merced, and I'm also very much affiliated with Texas Space, which is an organization, a company, an LLC that is very much on the forefront of this kind of research, looking for alternative forms of propulsion, gravitational wave communication, and even extraterrestrial type considerations and all of that good stuff. So I tend to be a little bit more, I'll admit, on the conservative side. So this very much will be like an actual just physics talk, like you might see like at a typical conference in a sense, but discussing possible ideas toward propulsion. I have a bunch of research ideas. Like I just heard Gary talk about all those ones. I don't have 20 years under my belt, so I don't have 20 topics, but I do have a lot. And I've knocked out quite a few of them here in APEC talks, like these ones here on gravitational Faraday-like flux rules. I'm going to revisit that in more detail today. I've looked at new formulations of gravito-electromagnetism, but gravitational waves are really a favorite of mine. So I was excited to hear that Gary has a extensive background in that. I'd love to know more about that. What I'm going to be focused on more today is quantum coupling between electromagnetism and gravity. Particularly looking at London's theory of superconductivity in the context of curved spacetime, gravito-magnetic Meissner effect in a superconductor. And right here, the green is where I'm going to be camping out a little bit more today, which is on quantization of gravito-magnetic flux by a superconducting ring, and Ginzburg-Landau theory in curved spacetime, and the possibility of gravitationally induced propulsion of a superconducting ring. So that's kind of the last topic at the end of my talk that I think ties in the most, of course, with APEC being an organization focused very much on propulsion. There are a bunch of other topics I'm interested in. I'll just really quickly sort of lay them out. I'm very interested in gravitational wave detection, generation, transduction, quantum effects associated with gravitational waves. So I've published quite a bit on those particular topics, and that was what my PhD focus was on. Lately, I've been looking a lot at the Aharonov-Bohm effect, both electromagnetic and gravitational. An older topic that I haven't revisited in a while is fluctuation dissipation theorem. More recently, I've been focused a lot also on the coupling of the, well, actually, this topic is an older one as well, coupling of gravitational field to the expansion of the universe. That was a study I did with Dr. Lance Williams. And we were also having a lot of great conversations with Jim Woodward. Dr. Woodward is a great friend, and he is very much obviously interested in that topic. This here is where I've been focused a lot lately. It's not going to be in this talk, but dark energy, dark matter, a little bit on quantum gravity and the cosmological constant problem. So I mentioned all this because basically if I'm invited back to APEC, there's a lot of stuff I'd love to talk about, but I am trying to focus a little bit more on propulsion because I know that's what APEC is mainly about. So that's going to be kind of my focus here. So my talk is coming mainly from this paper that I published some years ago. I think it was in 2021 or 22 on superconductor Meissner effects for gravito-electromagnetic fields in harmonic coordinates due to non-relativistic gravitational sources. And as I've said before, there's kind of a mouthful of a title. But the reason I chose that title is because there's a lot of particular choices that were made here, particularly harmonic coordinates and non-relativistic gravitational sources. And I would like to expand that research later into extensions that don't involve harmonic coordinates and allow for relativistic gravitational sources. So I just wanted to like pinpoint the topics that are found in this particular paper. It was published under this general heading of interaction between macroscopic quantum systems and gravity. So the editors included Modenese, who I know has spoken here before in APEC. Dr. Papini is also a huge figure in this field, and Dr. Tajmar, as I know many APEC are familiar with him as well, especially his excellent experimental work, which, as you'll see in my talk, a lot of the theory that I lay out is sort of left open-ended with the question put out there to experimentalists pertaining to what parameters can we feasibly achieve in the lab, like the size of quantum systems and things like that, because that will ultimately determine the numeric predictions that the theory that I'm going to share with you would predict. So going on from there, the abstract for this particular talk, I wanted to emphasize what it was. I did notice, like in the YouTube description, there was a previous talk abstract appearing there. So I just want to make sure we know what I'm talking about right here in this particular talk. So in the last one I gave, I showed that a superconductor can expel the gravito-electromagnetic field just like it expels electromagnetic fields in the Meissner effect. And so in this talk, the formulation is going to be extended a little bit further to talk about what's called the gravitational flux quantum, or fluxoid, in the body of a superconductor. I'll talk a little bit about the possibility of using low Earth orbit satellites to perhaps measure these effects. In fact, I just put out a paper with some colleagues and friends who looked at the Aharonov-Bohm effect, and that experiment also required the usage of satellites like the International Space Station and such. So the whole idea of doing experiments on satellites can be very helpful in the context of gravity. But I also like to look at what we can do down here in a lab. So the main system that I'll suggest that we look at is a rotating massive cylinder, which could potentially produce what I'm referring to here as a motional gravitational EMF and a transformer gravitational EMF, and possibly even lead to propulsion with like an experiment that will kind of mimic the jumping ring effect. Like for anyone who's like a physics teacher like me, one of the things you do in your classroom is you show like the jumping ring, where you have a ring around a core, usually like an iron core, and you hit the switch on a mechanism that produces a current there, and you have a ring that shoots up in the air. And it's using the magnetic field of that coil around the iron core to propel the ring. The question is, can we use the gravito-magnetic field to produce such a propulsion as that? Because that would most definitely be a new, if you wish, alternative form of propulsion that we, to my knowledge, have not seen before. Okay, so much of this work that I've done is based on a paper by Bryce DeWitt that he published back in 1966, referred to as Superconductors and Gravitational Drag. So that's DeWitt there with his arms folded. He looks like a pretty serious guy. Did a lot of phenomenal physics, wrote volumes on quantum gravity. Not sure if you recognize the guy next to him. That's Kip Thorne, many moons ago. And I'm sure other great physicists there in the room. Now, that paper is kind of like a foundational paper on this topic. And so it's sparked a lot of interest for decades, really. I mean, there's papers published on these topics all the way up till now, since 1966, so many decades. Interestingly, it's a pretty short paper. It's a physical review letter. There's only 11 equations, but I have personally seen it referenced many, many hundreds of times and seen it hailed as essentially a founding paper on this topic. So quick rundown, I talked about this in my last talk, but I'm going to lay down a few of the items from that paper because we're going to use them again here in this talk. This is the Lagrangian that DeWitt starts off with, which is pretty much a standard Lagrangian for a relativistic charged massive particle in the presence of an electromagnetic field or electromagnetic force potential. So the Hamiltonian is quite nasty. It's quite a bit of a challenge. At least I found it to be a bit of a challenge to derive it. I took quite a bit of time from the beginning of my PhD just trying to rederive what DeWitt did. And so you can see it involves components of the metric. and sort of like a minimal coupling rule coming in there, like a momentum minus an electron charge vector potential, pretty standard in minimal coupling rule for electromagnetism. So what DeWitt did is he took the weak field limit and the slow-moving particle limit, non-relativistic, and claimed that you arrive at that Hamiltonian. I did show in my previous talk that I do claim that there is some errors with this limit, the weak field limit, and I hesitate to object to anything the mighty DeWitt has done, but I've gone over the math over and over and shared that with multitude of colleagues and published on this, and there are errors there. But that's a previous talk that I already went into detail on. The main thing that really matters here is, physically speaking, you get this extended minimal coupling rule, which is in fact true. You have not only now the vector potential, but now this gravito vector potential that comes in the minimal coupling rule. And DeWitt defines this G vector, which is essentially just a linear combination of the magnetic field and the gravito-magnetic field. And so he gave it the name G vector. I don't know why. But what DeWitt claims then is that it's not just the magnetic field, but it's this G field that's expelled from a superconductor. And as you can see, that means that the gravito-magnetic field, B sub G, that we have there, would also be expelled, not just the magnetic field. So he predicted, DeWitt that is, predicted that there would be an electric current that would be induced in a superconducting ring when it's in the presence of a gravito-magnetic field that's produced by a rotating massive cylinder. And I'll show kind of a picture, some diagrams of how that would look. And so this is the current, the electric current that he predicted. And again, to be totally honest, as you'll see in this talk, I do object to that expression there, and I'll explain in detail why I think it's actually not correct. All right, so but continuing on with the key insight that DeWitt had for us, which is that, as we know, when a superconductor drops below critical temperature, the magnetic field is expelled from the superconductor. And so what DeWitt predicted is that the gravito-magnetic field would also be expelled from the superconductor. And that actually opened up a lot of controversy. There's a lot of papers that both dispute and support that claim. And I spent a lot of time in the last talk explaining why there are issues there and what the bottom line is. So I'm just going to remind us of what the bottom line was. So it is true, I'll tell you this, the bottom line, it is true that you can expel a gravito-magnetic field from a superconductor. And so all the phenomena that we see with superconductors, like flux spinning and levitation and things of that nature, all can involve the gravito-magnetic field just the same way they involve a magnetic field. And that's pretty phenomenal in itself, because that's definitely a new gravitational effect that is very much at the cutting edge of gravitational physics and hopefully even propulsion. I mean, you can see levitation is definitely on the way to propulsion. So now, as I say here, not so fast, because there are contradicting results in a multitude of papers. I counted at least 18 written collectively by more than 20 authors, published over more than half a century, basically debating this. And so I kind of took it upon myself as a mission, I guess you could say, to figure out what the bottom line is. And as it says here, some say you can expel the gravito-magnetic field, some say you can't, and some say maybe with special conditions. I landed on it's maybe with special conditions. So let me lay out a little bit of the math. Here's a metric just in flat space-time, so your Minkowski metric. As many of us know, in general relativity, we can introduce what's called a perturbation to the metric, and it basically can be thought of as the gravitational field or potential, whatever you want to call it. And it basically describes how flat space-time can be expanded or contracted or warped in a variety of ways. So this is my general relativity in a nutshell slide. I already kind of chatted a little bit about it in the last talk, so I won't spend much time here. Just reminding us of standard general relativity. You got to construct the Riemann tensor from the metric and contract indices to get the Ricci tensor and the Ricci scalar. And from there, you construct the Einstein tensor. And then Einstein's genius was to basically mesh that with the stress energy momentum tensor and come up with the Einstein field equation. Here it appears with the cosmological constant, which I won't be worried about in this talk because it's very small and it's not relevant generally to lab scale physics. Okay, so the particular formulation of general relativity that I'll be looking at is in harmonic coordinates, where you can basically get things to look a lot like electromagnetism. You can define a gravitational 4 potential that's a lot like the electromagnetic 4 potential. You've got this scalar potential and vector potential that are again similar to electromagnetism. You've got a wave equation, though, as I spent quite a bit of time talking about this 2 talks ago for APEC, that we don't want to think that that means that you get gravitational waves out of that equation. And there's a lot of papers that have incorrectly sort of gone full-fledged, working out all the physics of gravitational waves from that wave equation, and it can be shown that, unfortunately, it's a mathematical mirage. In fact, a colleague of mine, Dr. Lance Williams, who I mentioned, and myself, wrote a paper called Maxwellian Mirages in General Relativity. But nonetheless, this formulation is really handy because we have a lot of intuition about electromagnetism, perhaps compared to gravitational fields. So you've got this gravito-electric field and this gravito-magnetic field defined very much the same way as we do in electromagnetism. I'll be working with the ideal fluid stress tensor, which is common in this context. In the non-relativistic limit, you basically just have your rest energy density, your momentum density, if you'd like to, or mass current density, if you'd like to think of it that way. And you pretty much just ignore the rest of the stress tensor, the spatial piece. So this is just kind of pointing out the notation I'll be using. J will be your usual current density, but it's a mass current density. And in the context of what DeWitt did, DeWitt looked at what was called a stationary mass current, or if you wish, a time-independent metric. So basically, technically, that last term in the gravito-electric field would be 0 in DeWitt's formulation, and there therefore not be any gravito-Faraday law in the context of what DeWitt did. So here's sort of like the sort of the framework that we're working in to look at what DeWitt did. And again, I remind you that there was no Faraday law, and that also means that one of those terms in the gravitational Lorentz force is 0. And for a stationary mass current, you don't even have a gravitational displacement current there. So it's a very, very restricted context that DeWitt worked in. So with that in mind, starting out with that same Lagrangian, but now working out the canonical momentum in detail. First, I'm expressing the usual Lorentz gamma factor in terms of the metric in curved spacetime. But basically, working out the canonical momentum in the usual way of taking the derivative of the Lagrangian with respect to the velocity, you find that you get this expression. So this is not as simple as the one I showed you DeWitt had, but it does reduce to what DeWitt had in the appropriate limit. But I'm not going to reduce it yet. I'm going to keep it in its full glory. Mind you, I'm still in linearized GR, so first order in the perturbation, and it's still slow. It's actually not necessarily slow-moving particle because you see the gamma is still there, so it can be a relativistic particle, but it's still the weak field limit, and I've kept all the electromagnetic stuff in there. So that's basically what I'm going to suggest is like the general minimal coupling rule that we can use for everything that's to follow. So it's boxed for that reason because that's what we're going to work off of. So now looking at a superconductor. So the supercurrent comes from the canonical momentum. Even if you don't have gravity in the mix and you're just looking at standard superconductivity, you start generally with the canonical momentum if you're looking at like a London theory of superconductivity. And so when you apply the momentum operator on this Ginzburg-Landau complex order parameter, that's what that capital psi is. It basically characterizes the Cooper pairs that you would have in a superconductor, which are the electrons that are acting quantum mechanically, sort of like waves. So that's what that psi is. It represents the electrons in your superconductor. And deep in the superconductor, you find that the Cooper pairs are in a 0 momentum eigenstate. So what that means basically is that when you work out your supercurrent velocity from the canonical momentum that I had in the previous slide, you get this supercurrent velocity, and it leads to a current density. If you just define current density in the usual way, which is in this case, like the first current density there is just your charge current density. So it's got your number density ns multiplied by your charge, which would be like the electron charge. That's why the minus is there, so that when the Q is turned into an electron charge, it becomes a positive current, which is the conventional current. But then you also have that mass current over there as well, okay? And that would involve the mass of the Cooper pairs. So with that in mind, it turns out then that the supercurrents end up being represented by these two expressions where this capital lambda is actually a constant that the London brothers defined when they were working out London theory of superconductivity. The alpha and the beta, I define them just to clean up the expressions so they look kind of nice. See how they're nice and symmetrical? They both have like an alpha, A vector minus beta, H vector. So they look nice now. Theoretical physicists are all about making the math look nice if you can help it. All right, so here's the idea basically is that if you start with Ampere's law, good old Ampere's law, and you just plug in your typical supercurrent there from the London constitutive equation that comes out of this formulation, then you get the standard Yukawa-like equation that predicts the Meissner effect. And that minus sign in particular is what ends up giving you an exponential decay solution and hence a penetration depth. Well, the interesting thing is if you play that same game for gravity and you start with the gravitational Ampere law and you use the mass supercurrent and you plug it in, you get a plus, which means you don't get an exponential decay solution. You're going to get a sinusoid. So there's no exponential decay of the gravito-magnetic field. That's why a lot of papers say it doesn't happen because of that red box right there. But it turns out, interestingly, if you keep magnetism and gravitomagnetism both in the system together, don't look at them independently, but have a system that involves them both, you're going to get these coupled differential equations. And I spent some time talking about this in my last talk, so I won't go into it so deeply right now. But basically, when you decouple them, you end up finding that, granted, if you set the magnetic field equal to 0, you don't get expulsion of the gravito-magnetic field. But if you keep the magnetic field around, then you do get expulsion of the gravito-magnetic field. And in fact, the penetration depth of the gravito-magnetic field ends up being approximately the same as the penetration depth of the magnetic field. So it's basically an effect that's right on par with the Meissner effect. It's just a gravito-Meissner effect. Okay, so that was pretty cool to find. So the summary here was basically, if you have a superconductor, of course, it's going to demonstrate the Meissner effect. Magnetic field's out, expelled. If you have only a gravito-magnetic field, it's not going to be expelled. But if you have them both, then they will both be expelled. So that was the bottom line there. Now, that kind of brings me up to where I really want to focus on this talk, on the sort of basically second half of the paper I published, which also is dissecting the second half of DeWitt's work as well. So going back to the minimal coupling rule, just in standard superconductivity, which basically just involves the canonical momentum minus q a vector, where the canonical momentum is promoted to an operator. Ginzburg-Landau theory shows us that you arrive at this supercurrent density that involves the complex order parameter, that capital psi. And notice the last term there is there because of the presence of the vector potential. So that's because of the presence of magnetism there. Now, if you use the minimal coupling rule that I showed earlier, the boxed equation I had earlier, you can arrive at a similar supercurrent density, but now that last term has this C vector, where the C vector involves not just the magnetic vector potential, but the gravito-magnetic vector potential H, and it even has the scalar potential in there, the phi sub g. So there's a whole bunch more coupling that comes in, not just electromagnetism, but now gravity is coupled in to the superconductor. That's the takeaway from what you're seeing here. Now, again, do the same thing as you normally would do in superconductivity, like in a standard book on superconductivity. You'd write down the complex order parameter involving the number density ns times some phase quantity, the e to the I phi, where phi is the phase. And you'll find that the supercurrent then reduces to that expression that I showed there. But notice that now you've got that C vector at the end there. So deep inside the superconductor, where the supercurrent and the supercurrent velocity are 0, you can set J and V to 0, and then you find that you arrive at this expression here involving the gradient of the phase being related to all the fields that we're talking about. Now, on that left side, because the wave function is single valued, or putting it another way, if you apply the so-called Byers-Yang theorem, we know that if you were to do a loop integral around a closed loop of the gradient of phi, you've got to get an integer of 2 pi when you make your way around. Otherwise, the wave function is not single valued, which is kind of like one of those premises of quantum mechanics that is always assumed generally to be true. So on the right side, if you apply the line integral there, and then you got to use Stokes' theorem, you're going to arrive at the magnetic flux in the first term, the gravito-magnetic flux in the second term, and then this weird third term that involves the cross product of the gravito-electric field, like what we would call like Newton's field that holds our feet to Earth, crossed with the vector potential. It's kind of an interesting term, and it doesn't appear in the literature anywhere, but when you walk through the math, it's there. Now, mind you, by the way, you might notice it's on the order of 1 over c squared. So if you're going to go non-relativistic, you would throw it out. So now here's the idea, is that if we're going to try to talk about a system where we could see this happen, we'll bring in like a solid massive cylinder. This is exactly what DeWitt looked at, and it's spinning. So in a sense, you've got this mass current density. It's like a mass current because of the rotation, and it's going to generate a gravito-magnetic field, just like you would learn in magnetism. The only difference you might notice is there's a minus sign in the gravito-ampere law. So interestingly, it turns out that the mass current density rotates in the opposite direction of the gravito vector potential. Just kind of an interesting feature that comes out of general relativity, and it still satisfies the continuity equation for conservation of mass current. Anyway, so that's the concept, that's the system that DeWitt had in mind in his paper. And I mentioned this in our previous talk, that the best I could find for a system that exists, that actually exists, that could possibly be used for an experiment like this, was the world's largest flywheel power storage system using a superconducting magnetic bearing. And I believe it's in Japan. There's the website there if you want to check it out. And it's pretty huge. I mean, you can see to scale, there's a person there, right? And so it contains CFRP, carbon fiber reinforced plastic. It's 2 meters in diameter, so that's why it's like the width of the size of a person across there. It weighs 4 tons, and they spin that thing at 6,000 RPM, which I think is just wild. I don't think I'd honestly want to be in the room in case the bearing goes bad. I don't want to. Anyway, so that's the closest I could find to something really massive and spinning really fast, so that you could generate a very large gravito-magnetic field. And if you work out the math, you start with Ampere's law, and you use Stokes' theorem, and you use the mass current and mass current density and so forth. You can evaluate the gravito-magnetic field that you would get out of this thing, and you could plug in the radius of it and whatever the mass density is of it, and omega in this case was like 6,000 RPM, etc. And mu sub g, as I showed on a previous slide, is just shorthand for Newton's constant g divided by or 4 pi Newton's constant g divided by c squared. Anyways, you can also work out the flux that you would get out the top, and the magnetic flux expression is shown there. And I put in some numbers for that giant flywheel system, and it comes out really tiny. That's why it's so hard to measure this stuff. It comes out to 10 to the minus 21 meter per second. That's the units for the gravito vector potential. So it's super tiny. That's the problem. And so you got to use as much mass spinning as fast as possible to try to get even the most minuscule effect out of this thing. Now, here's the idea basically, is that if you have, like, say, a superconducting slab that's above this giant mass cylinder, and you're trying to use the superconductor to detect this gravito-magnetic field, you might look for what you might call the fluxoid. So I'll remind us that basically in standard superconductivity, there's this magnetic fluxoid, which is the smallest magnetic flux that you can have in a superconductor because the magnetic flux is quantized. So, like, if you look at this expression I have here, if you ignore the flux of the gravito-magnetic field, then you have basically that the magnetic fluxoid is just h over 2e. That's well established. So this is the extra contribution due to the gravito-magnetic flux, and there's another contribution from the gravito-electric field, which would basically be like Earth's gravity, for instance. But you'll notice it's super duper tiny. I mean, Planck's constant squared in the top, c squared in the bottom. It's just really tiny. Now, what I worked out basically is that I looked at some papers, and it turns out that the size of a fluxoid is on the order of 10 to the minus 5. So you can work backwards and find your vector potential that you would get for that. And that makes that very last term totally negligible. It's like 10 to the minus 54 Webers. Okay, hopeless. So that only leaves us with that second term if we hope to see anything gravitational. And there, again, if you use that 10 to the minus 21 for this flywheel, then that second term I mentioned is still super tiny. It's 10 to the minus 39 Weber. Still pretty hopeless. So I looked at the low Earth orbit satellite, figuring we need a lot more mass. The largest mass we have around is the Earth. It spins slower, but it's a lot of mass. And if you work out the gravito vector potential for the Earth at the location of a low Earth orbit satellite, it's 10 to the minus 3, which is obviously way, 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 way better. And now if you make use of that value, you find that the gravito-magnetic flux term here comes out to 10 to the minus 18, which is obviously a whole lot better. But what it means is that if you take an experiment that's capable of measuring the magnetic fluxoid, H over 2E, it would have to have a sensitivity that's 10 to the 18 times more sensitive to be able to pick up this gravitational fluxoid. So it doesn't seem very likely, but this is part of the whole story, so it deserves mention because it also is relevant to where DeWitt goes with this. So where DeWitt goes with this is he says, okay, let's put a superconducting ring around that cylinder, and let's see what happens when we spin up that cylinder and introduce a gravito-magnetic field there. So going back again to the canonical momentum, promoting it as an operator, acting it on the wave function, but this time we're not going to require that all those fields vanish deep inside the superconductor because we're going to stay on the skin of the ring. So we're not deep inside a slab, we're on the skin where you can have fields exist because you're shallower than the penetration depth. So again, if you kind of crunch through here a little bit, apply the canonical momentum operator, take an expectation value, argue your way to something that looks kind of classical by using Ehrenfest's theorem. This is commonly done. And then take a line integral of everything. You're getting something that looks a lot like what we had earlier. But the difference now is, again, when you require the single valuedness of the wave function, now the expression is quite a bit longer. It's got more terms in there. On the first term there, you've got a current, and then you've got your fluxes, the magnetic flux and the gravito-magnetic flux. And then you've got, again, those two weird terms. Well, you got that first weird term. Now you have a second weird term, these cross product ones. And then it's all quantized by NH over 2 on the right. So now the J vector and the E vector can be non-zero because we're on the surface of the ring. We're shallower than the penetration depth. So these terms are zero for the fluxoid expression, but because that was in the body of the superconductor. Okay, so what DeWitt does is he drops terms that are of order C, 1 over C squared. So if I back up for a minute, you see basically that second integral, the whole thing is 1 over C squared, so you can just drop it. Okay, so he drops that. He also uses a little bit different notation. I mentioned this earlier. He defines this capital G vector, and it's the linear sum of your magnetic field, which he calls capital H. I've been calling it capital B, which is, I think, probably typically used in modern days more. And that second term in his G vector is his gravito-magnetic field. Okay, he just doesn't give it that name. He just calls it del cross H. So here's the crux of DeWitt's claim. He says that if H, the magnetic field, is initially 0, and by the way, your gravito-magnetic field is also 0, so like nothing's going on, then he says because the flux quantization condition, which by the way, that means, as he says, the flux of G through the superconducting ring, he says must remain 0. That's the part that I'd like to debate. I don't see why the right side of that equation has to remain 0. And if anybody can suggest why, I would love to hear it, but you'll see where I go with this argument. So anyways, DeWitt goes on to say, but since the gravito-magnetic field, del cross H, is non-vanishing in the final state, a magnetic field must be induced. So what he's saying basically is like, start with your cylinder spinning, and you've got a gravito-magnetic field going through the ring, and no magnetic field. And then he says, stop spinning the cylinder and now you've turned off the gravito-magnetic field, that's going to force the magnetic field flux to turn on out of the blue. So the point is, experimentally, what he's saying is that if this cylinder is spinning and you stop spinning it, all of a sudden you're going to get a magnetic field out of nowhere in the ring. So now, mind you, if you look carefully at what it's doing there, he's basically considering a system where every term is zero in the initial state, and then in the final state, he requires that the current density and N are still zero, but the flux is non-zero. So I should have said he spun up. He spun up the cylinder. I shouldn't have said that he turned it off. He spun it up. And so the point, though, is that he requires the current density and the N, the two far sides of our equation, to stay zero at all times. So putting it another way, if you require those terms to be zero, you get that equation that you see there. You have only the two fluxes. And now he's saying basically that they're linked. Those two fluxes are linked. And so if basically one turns on, then the other has to turn on also. So that's what happens. He's saying if you spin up the cylinder, you turn on the flux or gravito-magnetic field, suddenly you'll have a flux and magnetic field that has to turn on. And he goes a step further and he says, okay, let's calculate a current that's induced in the ring as a result of this sudden magnetic field. And so if you take a time derivative of, well, basically if you apply Faraday's law and definition of inductance, so the usual di dt is equal to -1/L d phi dt. So we're taking a time derivative of a flux, and then he's using that relationship between magnetic flux and gravito-magnetic flux to get this thing in terms of a time derivative of the magnetic flux. Because remember, that's what's going to change with time when you spin up the cylinder. And if you integrate and use the expression that I derived earlier for a massive cylinder, you arrive at this expression. And I worked out the numbers for the flywheel, and it's 10 to the minus 23 amps. Probably not going to be measured anytime soon. All right. So unfortunately, but he left it there. He didn't put numbers in. The boxed equation is where he left it. In fact, he even left several of those quantities that appear in there out of the formulation. So he has a result that's not actually technically in units of current, but he just has a proportionality there. I think he basically just has only the mass, the radius squared, and the omega, and the capital L. So he left out the prefactor and the script L. The script L is the length of that massive cylinder that's spinning, which is important. Okay, so what I'm claiming here is that I don't think it's physical to set the current density to zero and keep it that way. And the reason is this: if you start spinning that massive cylinder and you introduce a gravito-magnetic field, by doing that, that gravito-magnetic field is going to drive current in the superconducting ring. And keep in mind, we derived this whole thing using the canonical momentum, and the canonical momentum predicts that you get a supercurrent whenever there's a field. So it's unphysical to say I'm going to turn on a field but keep the current zero. I would also suggest that it's not physical to force the system to remain in the n equals 0 state on the right side, while on the left side, you are introducing fields. Because if the whole entire left side is quantized in units of h/2, which means that if the entire left side exceeds h/2, then the system is going to go to the next quantum state, n equals 1 or 2 or 3 or however much. Like generally in our classical world, n is very large. And so we don't even notice the jumps because they're so tiny. As we know, that's how quantum mechanics is, right? The quantum jumps are so tiny that in our classical world, we don't notice that happen. So I would argue it's not physical to force the right side to be zero. So what does that tell us then? So what I'm suggesting is this, is that we can take that whole equation and rewrite it in, I believe, a little bit more of a helpful way, which is I'm keeping my current density term, all the fluxes and such I'm putting into this quantity F for flux, and the right side's still the same. And so as you can see, I defined F as all the fluxes, your magnetic flux, your gravito-magnetic flux, and all the weird term flux there, okay? All of that's quantized in units of h/2. And now, if you want to talk about what's happening for the ring, your current density will exist in the skin of the ring. So that's why the current density is written here as the current divided by pi lambda L squared, because lambda L is the London penetration depth. And so you're only going to have current in that skin. And so if you plug that in, then you arrive at this boxed expression here, where d is the diameter of the ring, I naught is what I'm calling an electric current quantum. It's the smallest chunk of electric current that you can bump up by. It's analogous to the magnetic flux quantum, the phi equals h over 2e. So what I claim is this is really a constraint equation. You're not going to be able to generate one field from another, as DeWitt claimed that if I introduce a gravito-magnetic field by spinning up my cylinder, suddenly I'll be able to generate a magnetic field from that. It's not a field equation that links the two fields this way. Rather, it's a constraint equation that basically just says all the fields that you've introduced all together have to satisfy this quantization condition. So unfortunately, I don't think this induces a current in the ring. Now, there is a way to induce a current in the superconducting ring, and so that's what I look at next. So there's two ways to induce a current, or if you wish, an EMF. And this goes back to kind of just standard undergraduate physics. There's what you can call motional EMF because of having a loop in motion, for instance, or a time-varying boundary, essentially. And there's what's often called transformer EMF, where you have the field is varying with time. So it's not the boundary that describes the flux, but rather it's the field itself that's changing with time. And you can see this explicitly in Faraday's law, or what better is described as the magnetic flux rule, if you will. Because if you take the time derivative of the flux, and the flux is magnetic field B times area A times cos theta, then that time derivative can act on any of those three quantities. So for instance, if you work out your product rule and you just spread it all out, you've got three ways that you can generate an EMF. You can change the magnetic field with time, that's the first term. You can change the area with time, or you could change the angle between the loop and the field. So just to kind of bring it home, some common examples of that first term where the magnetic field's changing. You could have like a bar magnet with a loop that approaches it, or you could have a changing current in a solenoid that's near a loop. I mean, these are all just undergrad examples. For the second term involving the changing area, you could change the area of the loop, or you could things of that nature. So that's what we often call motional EMF. And then the last one is I'm not going to be looking at, but it's commonly what we use for generators or alternators, like in your car, which is basically the loop is rotating, for instance, and so you get an induced EMF that way. So if the pictures help, this is the idea basically, is that the dB dt is if you have your field changing, the dA dt is if you have your area changing, and then the d cos theta dt is if you just change the orientation there. I'm only going to focus on the first two, and the reason I'm talking about all this, even though a lot of this is kind of just fundamental physics, basic undergrad physics, is because I'm going to apply all this to the context of gravity, linearized general relativity, and gravitational version of EMF induced. So still a little bit more background. So as many of us know, the EMF is basically an energy. If you just take EMF times charge, it's the amount of energy associated with the charge going around, say, a closed loop, for instance. So you can take a line integral of the Lorentz force around a closed loop, and that could be defined as your EMF. And now we also know from the Faraday flux rule that it's the time derivative of the magnetic flux. Now, as I just showed, you can break that up into two separate quantities by the product rule, time derivative of the magnetic field or time derivative of the area. So then if you apply Faraday's law in that first integral, Faraday's law says the time derivative of a magnetic field gives you an electric field. And that second integral, if you play around with it, Griffith's textbook on electromagnetism shows a really cute way of showing that you can actually get that term to turn into a V cross B term, which is really beautiful, because then what you're finding is that the Faraday flux rule that we're dissecting here is actually directly connected to the Lorentz force, because we kind of like recovered the Lorentz force in a sense inside that integrand. So there's a connection. The main point I'm trying to make here is that there's a connection between the Lorentz force and EMF, and that you can break up the two pieces into what I was calling transformer EMF, where the magnetic field's changing, and motional EMF, where the area of the boundary is changing. Okay, so keep that in mind, because we're going to apply all of that now to gravity as well. So in the context of gravity, if we want a force like a Lorentz force, you got to start with the geodesic equation of motion, and using the same exact metric that I used earlier to derive the Maxwell-like equations for gravity, you arrive at that bottom equation, which is a Lorentz-like force. You got basically an electric-like term, a magnetic-like term, but then you've got this third term that just comes out naturally. It's also linear. It's also first order in the perturbation, and it's also first order in velocity. So it belongs there. You can't just throw it away and say, like, I don't like it because it doesn't look like Lorentz force anymore. Sorry, it's on the same order. And you'll also pick up a factor of 4 there if you're going to keep all your field equations looking the way that they do. Okay, so with that in mind, now we're going to play the same game we did in electromagnetism, but we're going to apply it to linearized general relativity. So in other words, we're going to take a line integral of that force and call it a gravitational EMF, and we're going to play that same game where you can break things up, like you can take basically your gravito-magnetic flux and you can take a time derivative, apply the product rule, and arrive at 2 terms that now look like a Lorentz force inside the integrand. So it's just like we did in electromagnetism. And so we have this like gravito-Faraday flux rule, if you wish, that shows up. And I remind you that, again, you've got a transformer EMF that comes from the electric piece, and you've got a motional EMF that comes from the V cross B piece. But we do have that third piece, which I would suggest is also a motional EMF there. Not emotional like I'm happy or sad, but a motional EMF, which is basically because there's a velocity there. So again, it has to do with motion generating an EMF. Okay, so with that in mind, then what we can do is look at the whole shebang in one shot. Write down the force equation that involves both gravity and electromagnetism. So on the left side, you've got your mass times acceleration. So that's your force. On the right side, your first term is your gravitational force involving the Christoffel symbol. That's just your geodesic equation of motion. And then the last term is your Lorentz force written in covariant form. Expand it all out. Take the lowest order approximation for gravity. Take the non-relativistic limit for your particle, so you only stay to order of v, not v squared, and you arrive here. So the beauty of this is we recovered in blue the Lorentz force, in red this like gravitational version of the Lorentz force, and in green a coupling between gravity and electromagnetism that appears there. Okay, and if you want, you can even go so far as to describe this like overarching EMF that you get from everything. An EMF from electromagnetism, an EMF from gravity, and an EMF from the coupling of gravity and electromagnetism together. Okay, so this giant EMF. Take this now to bear upon that experiment that we were talking about with the superconducting ring. And so in that experiment, if you take a look at the nitty gritty, like for instance, what do we have going on for the scalar potential? Well, it's basically mainly the scalar potential of Earth, because the scalar potential of the cylinder is going to be like infinitesimal compared to Earth. And even that of Earth is like 10 to the minus 9, as you can see there. So pretty much all the phi's, phi sub g can be ignored. Phi dot, the phi g dot could be ignored because the scalar potential of the Earth isn't changing with time. And then if you look at the direction of the fields and such, you actually end up eliminating practically everything except just those 2 flux terms. The magnetic flux term that we all know and love, and then this gravito-magnetic flux term. So that's really all that ends up really mattering here anyways. There's other cases, as I'll show, where those other terms that are interesting stick around, but not here. Now, I was trying to think about what are some ways that we could experimentally observe this. And so, again, as I mentioned, there's the motional EMF and there's the transformer EMF. So I started with the motional EMF thinking, okay, well, what if you just drop the ring in the presence of this cylinder so that basically as it falls down, it's going to experience a time-varying flux, gravito-magnetic flux, because of its motion. So basically, as it falls down in, it effectively experiences a stronger and stronger magnetic field. I did draw the magnetic field like it's straight up, but it actually bows out. So as it drops in, it does experience a stronger field than when it was higher up. So that would be one way. Another way I was thinking is if you oscillate the ring, and I wasn't savvy enough with PowerPoint to make it oscillate. So just pretend it's oscillating, and that's an option, you know. And so this is where I had some questions for experimentalists. Like, for example, is it practical to suspend a superconducting ring above a rotating massive cylinder? Can it be oscillated? And I even thought, what about if this system of an oscillating superconducting ring could be connected to a capacitor circuit? Because after all, what's going to happen here is you're going to generate a very weak induced current in the ring because the gravito-magnetic field is so weak, right? We saw that DeWitt's prediction, for instance, is very small, and that's very true. Even when you do things correctly, it's still very small. So I thought, what if, if something's being put out in tiny, tiny little drops, if you will, if you collect enough drops, you eventually have a reservoir of water, if you will, right? So I just thought, what if we could somehow siphon the induced supercurrent, the induced current in that ring, siphon it off to charge a capacitor so that at every cycle, like every time the ring comes down and it generates a current, we could siphon that off to a capacitor, and there could be like a switch that oscillates so that it disconnects when the ring goes up, reconnects when the ring comes down so that it again charges the capacitor some more, and it would just pump. It'd be like a pump that pumps the capacitor with charge. That, I imagine, would be a way to demonstrate the presence of the gravito-magnetic field. Because at this point, by the way, I know we all want propulsion, and if it were to be produced gravitationally, that'd be amazing. But at this stage, we can't even really demonstrate that the gravito-magnetic field exists in a lab setting, let alone try to utilize it to propel things. So this, I was thinking, would be a way to do that. And this is where I'd love to hear from experimentalists, like what size ring would be practical? Of course, the larger the better, because you get more flux. What frequency of oscillation is possible? And again, the higher the frequency, the sooner you're going to charge up your capacitor. So those would be ideas that I didn't flesh out the mathematical details here because those parameters are going to play an important role in the approximations that we apply. Now, that's the motional EMF. Another way, by the way, is if the ring could expand. I figure that's less realistic because superconducting material, they tend to be metals and such, so it's probably not very likely, but I threw it in for good measure because that technically is another way you could change the flux in there. Now, that's all motional EMF. Then, so again, questions, could we expand a ring like that? Can that even be oscillated? What kind of configuration could we set up? But the transformer EMF, I thought, would be more realistic. And so remember, the transformer EMF has to do with changing the field, not changing the geometry of the ring or the positioning of the ring, changing the field. And changing that field involves, of course, changing the spin of that massive cylinder. So in other words, if we had a time-varying rotation of that cylinder, we could produce a time-varying gravito-magnetic field in the ring. That would be a transformer EMF. So again, I wondered, is it practical to have a massive cylinder sped up repeatedly? Can it even oscillate in its rotation? What frequencies would be possible? What mass and what charge could we put onto that cylinder? Those would all be experimental questions I'd love to hear about if anybody has ideas. But I have a couple more topics to hit in the last 10 minutes or so that I've got. So you can also look at what you might refer to as a gravitationally induced Hall effect. So for those familiar with the Hall effect, basically, if you have an electric current that exists in a wire and it's in the presence of a magnetic field, the magnetic field will tend to cause positive charge to accumulate on one side of the wire, negative charge to accumulate on the other side of the wire. That's the green and the red, respectively. And so you'll get a polarization electric field across there. And then what will happen is basically the positive charge wants to move to one end, the electric charge wants to move to the other, but the polarization field will counterbalance. And so the bottom line is you get this steady state situation, but you get a Hall potential across the two sides of the wire. That's in a nutshell the Hall effect. So we'd like to see if there's a gravitational version of this. So I'm denoting the width of the wire, or the diameter, if you wish, of the wire with W. And E sub P is the polarization electric field that you would have there. And so the Hall potential could be approximated to be W times EP, treating it like a uniform field for simplicity's sake. So here's the idea. Go back to that full force that involves the Lorentz force with E plus V cross B, the gravitational Lorentz force, and the coupling between the two of them in the green there. Again, take a look at this particular configuration, and if you work out all the details, you'll find that you actually only end up getting the polarization electric field appearing in there, the magnetic field, the gravito-magnetic field, and then this last term that came from the coupling from the green box, which is the gravito-vector potential and magnetic field. So that's like a coupling between electromagnetism and gravity that would be there. Now, as I said, in the Hall effect, that force becomes basically becomes zero because you get a steady state situation where the polarization across the two sides reaches a maximum value and stays that way, and so you have no more net radial force acting on either positive or negative charges that are inside the wire. So setting the force to 0 and solving for E sub p and using current density as this supercurrent, the number density of the supercurrent particles, the Cooper pairs, and then also use the London penetration depth, because again, the current would only be on the skin. Anyway, so when you work it out, you get this for the polarization electric field. And now I popped in a bunch of expressions using the magnetic field from our massive cylinder, the gravito-magnetic field, the gravito-vector potential, pop it all in and work out your Hall potential, and it comes out to this. So again, this is where I would love to collaborate with experimentalists. If anybody is interested in these types of effects, we would have to work out like what are practical, realistic values that we could have for the charge density of our cylinder, the mass density of our cylinder, the length of it, the width across the superconducting ring, the radius of that ring, and then the angular frequency of the spinning mass cylinder. Those are all parameters that when we put them all in there, we would like to see, is there any hope of seeing something that could be practically observed in a lab? Mind you, it's all going to be super tiny, because you see here that that second term that has the g over c squared, that's the gravitational contribution to this whole thing. And so that's the reason why it's a very small correction term that you would have. Of course, if you just take away the charge density of the cylinder, you could get rid of rho c and be left with only the gravitational part, but you're still trying to detect something very small nonetheless. And lastly, this is kind of probably the closest tie to propulsion that I think this whole story entails, which is the jumping ring idea that I mentioned near the beginning. So if you have a ring, a superconducting ring, or really any ring that can contain a current, any conductor, and you introduce a gravito-magnetic field, just like as if you introduced a magnetic field, then you will induce a current in the ring, and then the ring will be propelled upward. Now, for magnetic fields, of course, they can be very strong, so you can actually get the ring to shoot up into toward the ceiling. It makes it a fun experiment or demonstration for students. With the gravito-magnetic fields, probably not going to be quite as exciting, because at best, probably you would just detect a lessening of its weight. Like if you were somehow measuring its weight, and then you introduce the gravito-magnetic field, you probably get a lessening of the weight. But again, small steps for small feet is what my PhD advisor Raymond Chow used to always say to us, and I heard he got that from Feynman. So I always think of that. If you could at least start there, then you can start to think about how you can amplify the effect and actually maybe even get to propulsion. So it would be like this jumping ring experiment, but because of the gravito-magnetic field. So if you look at the details, starting in the same spot again with the full entire force there, again, just kind of maybe choose an electrically neutral mass cylinder, so you can focus just on gravito-magnetic field, and then you can work out the differential force that you get, which is this green arrow that points straight up. It's the vertical component of the differential force dF that you would get, and it satisfies this expression here. Again, very small. You got mass of the electron over charge of the electron times the gravito-magnetic field, and then you're just going to integrate around the perimeter of the ring. And then I went ahead and put in the expression for, again, the gravito-magnetic field of a mass cylinder and integrated, and I arrived at this expression. So again, this would all depend on how massive a cylinder we could have. That's your M. The radius of the ring, the omega is how fast you're spinning that massive cylinder. L is how long it is, and the current I is the current that you have in that ring. Now, I should mention, we do have something going for us here, which is that current in the ring doesn't have to be induced by the gravito-magnetic field. You could potentially just externally introduce a current in that ring in the usual way that we produce electric currents. And so in principle, you could produce a very, very, very high current, and that would help the force that you get from the gravito-magnetic field to be amplified. So it kind of made me wonder, okay, well, if since I doesn't have to be induced here, it could be any value supported by a superconductor, or for that matter, it could even be a normal conductor. In fact, you might want to have the least massive ring possible so that you could get maybe the most propulsion out of it, of course, but obviously we just want to get the force to be as large as possible. But if you just want to at least measure something, having the lightest ring with the largest current in it possible would be ideal. So I did look up what are the highest electric currents that have been achieved in superconductors, and I found this Oak Ridge National Lab achieved evidently in 1996 the world record for the largest electric current density of 2 mega amps per centimeter squared in a superconducting wire. So I thought, okay, this sounds like some pretty high currents that exist out there. So maybe if something like that were to be utilized, that would give an additional advantage in trying to actually measure this, maybe not propulsion, but at least lightening of the ring. Even if you got levitation, that would be amazing. But at this stage, basically the experiments haven't been able to even make that much headway. So that concludes pretty much all the topics that I wanted to talk about that I mentioned is in the paper that I had published. So in fact, I can maybe mention from that slide again that if you want to read more about the details, you can find the paper here. It's open access on Frontiers, and I work out a whole bunch more details there than I talked about here in this talk. And so you can check that out if you would like. And you can, of course, just correspond with me directly if you'd like to talk about this. So I'd just like to conclude by thanking Professor Raymond Chow, my PhD advisor, for some great discussions. Professor Douglas Singleton and Gerardo Munoz from Fresno State, amazing physicists. Dr. Ahmed Farag Ali, a close friend of mine and an excellent researcher. Dr. Lance Williams as well, excellent researcher and a great friend. The support from Texas Space, an incredible organization. Juan Faria is our CEO, doing an awesome job trying to push this kind of research forward and get funding for us. And then, of course, Tim Ventura and the APEC community for inviting me to share this research with you.